Hello friends. So in today's lecture we will continue our next part. Okay. So in the last lecture we have learned what is partition of a interval and the length of the interval. So now we will see what is the mean by norm or mesh of the interval. Okay. So I have written the definition of norm. So what is norm? The greatest of the length of the segment of partition P is called norm or mesh of P. That is, suppose let we have a interval and some partition of that interval. Okay. So take the interval I is equal to 1 to 5. Okay. So we have taken a closed and boundary interval 1 to 5. Take some partition P. So take some partition P1 say. Okay. So partition P1 is equal to 1, 2, 4 and 5. Okay. This is the one partition of this interval I. Now this partition divide this interval into smaller segments or subintervals. So we know that. So what will be the first segment is from interval 1 to 2. So this is the interval 1 to 5, and this partition divides this interval into smaller segment. What is first segment? 1 to 2. Okay. So 1, here is 2, here is 3, here is 4. Okay. So first segment is 1 to 2. So this is the first segment 1 to. What is the second segment? 2 to 4. So 2 to 4. This is the second segment. And last segment is 4 to 5. 4 to 5. Okay. So this partition P divide this interval 1 to 5 into 3 segments, in which first segment or first subinterval is 1 to 2. So I1 is equal to 1 to 2. Okay. Second subinterval is 2 to 4. Okay. So I2 is equal to second subinterval 2 to 4. And the last segment I3 is 4, 5. Okay. Now what is the length of this segment of this subinterval? Is 2 minus 1, that is 1. So length of, we denote the length of first subinterval I1 as delta x1, and which is equal to 2 minus 1, which is 1. Now length of second segment or second subinterval is denoted by delta x2, which is equal to 4 minus 2, which is equal to 2, and the length of last segment is delta x3, which is equal to 5 minus 4, which is equal to 1. Okay. Now what is the norm of partition? The norm of partition is nothing but the length of segment of greatest length of segment of partition. Okay. So what is the greatest length of segment? Here the length of first segment is 1, length of second segment is 2, length of third segment is 1. So greatest is 2. So the norm of this partition is 2. Okay. So the greatest length of the segment of partition. So the norm of this partition P1 is 2. Understand? So here norm of partition P1, which is also noted as mu of partition P1 is equal to maximum of 1 and 2, which is 2. So which is equal to 2. Okay. So this is the concept of norm or mesh of a partition. Okay. So friends, the next term is refinement. Okay. So what is the refinement? It is adding something new in original partition. Okay. So definition is the partition P star is called refinement of P if P star, which is new partition, which contains original partition P. That is, we can say P is contained P star. Then P star become refinement of P. Okay. These are two similar things. P star contains P or P is contained P star. Okay. So we say that P star is called refinement of P if it contains original partition. For example, consider the interval I, which is closed boundary interval from 5 to 8. Okay, and we take partition P1, okay, as 5, 6 and 8. Okay, we have taken this partition. If we take P star as 5, 5, 5, 5, 6, 7, 8, then this P star become refinement of partition P. Why? Because P star is obtained by adding some extra element to P1. See, 5 is here, 5 is here. Then 5.5 is not here but added here, extra one. Now 6 is here, 6 also is here. Now we add some extra point 7, but the added points are again from interval 5 to 8. They are not from outside the interval, and 8 is in P1, also is in partition P star. Okay, so this 5, 6, 8, all these 3 points are already here, but we added 2 extra points, 5.5 and 7. We add these 2 extra element or point in this partition P star. So this P star become refinement of P1. Why? Because this P star contains this P1. Okay, this is the concept of refinement. Now the second term, common refinement of two partition. Okay, suppose again this is our interval 5 to 8 and we take two partition for this interval. We know for any interval we can find infinitely many partitions. Okay, so this is our interval I is equal to 5 to 8 closed and bounded interval. Okay, so we take partition P1 as it is 5, 6, 8. Okay, 5, 6, 8, and we take another partition P2 which is 5, 7, 8. Then the common refinement of partition P1 and P2 of the same closed boundary interval A to B is given by their union. That is, P star is equal to union of these two partitions. Okay, so what will be the common refinement of these two partitions? Just take the union of that two partitions. Okay, so now here P star becomes 5 is here, 5 is here, so take 5 only once. So we have taken 5 here, then take 6. So why? Because we have taken union. So add all the points, only add those points which are repeated twice, take only one time. Okay, so 5, 6, then 7 and 8. This become common refinement of these two partitions for the interval 5 to 8. So understand the concept of common refinement. Okay, so next point is Markov upper and lower sums. Okay, so we have to get the actual definition of Riemann integral. Okay, for that purpose this upper and lower sum are very much important. Okay, now we will see definition first. So we have given a function from an interval I to R. Okay, they are bounded function. So we have given a bounded function from some interval I to R, where I is a closed bounded interval from A to B. Okay, suppose P with any partition. Okay, so we have taken a general partition containing n element. Okay, so n plus 1 element x0, x1 up to xn. This is the partition of this interval I. Now, since our function here is bounded function, that is, function has some upper bound and lower bound. Okay, since function is bounded on whole interval, then function must be bounded on each subinterval. See, suppose this is the graph of function and this is our function. Okay, graph of function. Now this is our interval a to b. Okay, now see, in this interval this function is bounded. Why? This is the upper bound. Okay, this is the maximum value of function in this interval, and this is minimum value of function in this interval. So we have taken just idea. We have taken one example of bounded function. Okay, which has upper bound, say some point e, and a lower bound. This is lower bound, say f. Okay. So this is the bounded function. Now since this function is bounded on this whole interval, this must be bounded on its segment or some subinterval. Suppose this a to some point, say this is x0 to x1. So in this interval, function also bounded. Why? This is the upper bound and this is the lower bound. Again, from in this subinterval, again function is bounded. This is the upper bound of function, and again this is the lower bound of function. So if function is bounded on some interval, closure bounded interval a to b, it must be bounded on its subinterval. Okay. So see the notation. Capital MK means least upper bound of the function in kth interval. Okay. Similarly, small nk, okay, means greatest lower bound of the function in kth interval. That is, function की जो maximum value है in kth interval. So suppose this is the form A. This is the first interval. This interval function has maximum value. Suppose 4. Then capital N की value क्या होगी 4. Suppose again in this first interval, यहाँ पे हम M1 लिखेंगे क्योंकि हम first interval की बात कर रहे हैं. Okay. Now again in first interval, the minimum value of function is, ये minimum value of function की, suppose this is 3. Okay. So small m1 की value क्या होगी? Greatest lower bound which is 1. Which is 3. So this is the idea of capital M की, that is least upper bound of function in the kth interval and greatest lower bound of the function in kth interval. So then we denote lower sum of function f corresponding to partition P as sum of product lower bound, that is greatest lower bound, and length of the interval, and this sum varies from first interval to nth interval. मतलब पार्टीशन में जितने इंटरवल होंगे उतनी हम सम लेंगे. So sum varies from k is equal to 1 to m. Okay, m की delta x थी. Now if you replace this small m by capital M की, this will become upper sum. So upper sum, what is the definition of upper sum? Upper sum is nothing but the sum from 1 to n of product of capital M की, that is least upper bound of the function and length of that interval or segment. So we will get idea. We will clear the idea by taking the example. So this is called lower sum of f corresponding to partition P, and this becomes upper sum of f corresponding to partition P. Okay. So this is the definition of lower sum and upper sum. So lower sum लेते हमें क्या करना है? We have to take sum of product of. So first, suppose first interval, या फिर हम देख रहे हैं ये first interval है. Suppose इसमें function की minimum value क्या है? 3. Okay. So first interval m1 becomes 3. Okay. And in this case, what is delta x1? That is length of that interval. Suppose this length is 2. So delta x1 becomes 2. Similarly, we will get value of some value of m2, say 4, and length of intervals again, say second interval is 2. Suppose we have taken only 2 sub intervals, then lower sum becomes here. Now sum varies from here 1 to n because we have taken n intervals in this partition, that is n plus 1 elements. So here we have taken only 2 sub intervals, so sum varies only 2 times. Okay, after two terms. So first term is m1 delta x1. m1 is 3, delta x1 is 2. So lower sum is equal to 3 into 2. Now sum, so plus, put k is equal to m2 delta x2. What is m2? 2, delta x2 2. So 2 into 2. So 3 into 2 6 plus 2 into 2 4. So lower sum become 10. So we will take one more example to clear the idea of lower sum and upper sum. Okay. So now we will see one more example of lower sum and upper sum. Okay. So this is now we are directly given the graph of the function. Okay. So see the graph of function. We see the graph function is increasing. That is, we have given a increasing function and we have given interval closure bounded interval form 1 to 6. So we have to only focus on this interval. Okay. So this is the graph of interval, graph of the function in the interval 1 to 6. Okay. And we have also given the partition such that points are 1, 3, 4, 5, 6. So this partition divides this interval into segments or sub-intervals. What is the first segment? Is 1 to 3. Next 3 to 4. Next 4 to 5. And last 5 to 6. Okay. And we have also given the values of the function at some point. See, at 1, the value of function is 1. Okay. This height along y-axis is 1. So the value of function at point 1 is 1. Value of function at point 3 is 2. Okay. So this is the length on the y interval is the 2. Now value of function at point 4 is 3. At 5 4. At 6 5. Okay. So this data we have already given. Okay. Now you have to find upper and lower sum. So for that purpose we have to find three values. So we know the formula for lower sum. What is formula? Lower sum is nothing but the summation. Now summation over the sub-intervals or segment. So there are 1, 2, 3, 4 sub-intervals. Okay. Summation varies from k is equal to 1 to 4. Okay. There are 5, so 4 sub-intervals. Okay. So k is equal to 1 to 4 and greatest lower bound, that is mk, small mk, greatest lower bound into delta xk. Okay. That is length of the kth subinterval. That is, we can write this as m1 delta x1 plus m2 delta x2 plus m3 delta x3 plus m4 delta x4. Okay. We have written this in this notation. Okay. This is the summation notation and this is our time usual notation. So to find lower sum, you have to find m1, m2, m3 and m4. Similarly, length of first subinterval, that is delta x1, length of second subinterval, delta x2, length of third segment or subinterval, and length of last segment. Okay. So what is the delta x1? That is length of first segment. It is first segment is from 1 to 3. So its length is 3 minus 1. That is 3 minus 1, that is 2. What is the value of delta x2? Length of second subinterval or second segment is 4 minus 3. It's also 1. What is the length of third subinterval? 5 minus 4, 1. Okay. Then, sorry here. Oh, okay. And length of the last subinterval is 6 minus 5. It is 1. Now we have to find m1, m2, m3, m4. So what is m small mk? It is the greatest lower bound of the function where x belongs to kth interval. मतलब kth interval में function की minimum value greatest lower bound होती है small mk. So m1 क्या होगा फिर? So M1 means greatest lower bound of the function in first subinterval or first segment. So see the first segment 1, 2, 3. Okay, this is the first segment, and in this segment, this is the graph of function. We can observe that the minimum value of the function in this subinterval is at this point, at point 1. Why? So because function is increasing. Okay, so minimum value at we observe at point 1, and it's already given. This is given as 1. So what is m1 small m1? Greatest lower bound in first interval. Okay, which is 1. What is m2? M2 is nothing but the greatest lower bound or minimum value of the function in second subinterval or second segments. Okay, so second segment is 3 to 4, and minimum value occurs at point 3 c, which is given 2. So m2 is equal to 2. Then m3 is nothing but the minimum value of the function in third segment. This is the third segment. Okay, this is the graph function in third segment. We can easily observe. So at point 4, okay, at point 4, function has minimum value. So this is the greatest lower bound. Okay, and it is given as 3. So m3 is 3, and m4 nothing but minimum value of the function in last segment, which is 4. So we have collected all the required values. So just put the value here. We will get the lower sum of this function and for this partition. Okay. So lower sum LPF becomes m1 2 into delta x1. Delta x1 is 2. m1, so m1 is 1 and length of delta x1 is 2, plus m2 is 2 and length of second interval is 1, plus m3 is again 3, okay, and length of the interval is again 1, and last here delta x4 is 1 and m4 is 4, so 4 into 1. Now this sum becomes 1 into 2, plus 2 into 1 2, plus 3 into 1 3, plus 4. Okay. So the sum becomes 2 plus 2 4 plus 3 7 plus 4, so 11. This is the lower sum for this function here corresponding to this partition. Okay. Now similarly we will find out the upper sum. Okay, this is the lower sum. Now what is the formula for upper sum? Upper sum for partition P corresponding to for function f corresponding to partition P is nothing but the sum of product of capital MK and delta xk, where capital MK is nothing but the least upper bound or maximum value of the function in that corresponding subinterval. Okay, so we know value of length of all intervals. So delta x1 is 2, delta x2 is 4 minus 3 1, delta x3 is also 1, and delta x4 also 1. Okay, now we have to find m1. So m1, what is m1? m1 is the maximum value or least upper bound, okay, of the function in first segment. So see the graph. Maximum value occurs at this point. In the first interval 1 to 3, maximum value occurs at this point, which is given 2. So m1 becomes 2. Now in second subintervals, maximum value occurs at this point. Okay, at this point lowest value, and at this point at point 4 maximum value. Okay, since graph is increasing. Okay, and maximum value is 3. So m2 is equal to 3. In third subinterval, again graph is increasing. So maximum value occurs at this point, and which is given 4. So m3 is equal to 4. Again, in last segment, maximum value of the function is occurs at point 6, which is given as 5. So m4 is equal to 5. Just put this value in our formula. So upper sum becomes u p f becomes again m1 capital M1 delta x1. It is 2 into 2. Then plus summation from 1 to 4. Again 4 intervals. What is m2? 3. What is delta x2? 1. So 3 into 1. m3 delta x3. m3 is 4. Delta x3 is 1. So 3 into 1. m4 into delta x4. So 5 into 1. So this becomes 4 plus 3 plus 3 plus 5. So 4 plus 3 is 7 plus 3 10 plus 5 15. This is the upper sum for this function corresponding to this partition P. Okay. Now we will see some theorem. So sir, first theorem, a very easy theorem. So we have to prove that for any partition P of the interval, lower sum of the function corresponding to partition P is always less equal to upper sum of the function F corresponding to partition P. That is, upper sum always greater equal lower sum. Okay. So proof is very simple. So we have formula of lower sum. It is equal to sum of mk delta xk, where k varies from 1 to n, where n is the total number of subintervals. Okay. So summation mk delta xk, whereas this small mk is the greatest lower bound of the function. Okay. So we know that this capital mk is the upper bound, at least upper bound of the function in the kth interval, and small mk is the lower bound or greatest lower bound of the function in the kth subinterval. Suppose C. We know that this is our, suppose it is the function, okay, and this is our interval. See, what is capital M means? It is the least upper bound, okay, that is the upper value of function in that subinterval, and this is the minimum. This is the maximum value of the function. This is the minimum value of the function, and everyone knows that maximum value always greater equal minimum value of the function in the interval. Only if function is constant function, then upper value, that is maximum value, and minimum value are same. Otherwise, maximum value of the function in some interval always greater equal minimum value of the function. Suppose this is the function, this is the maximum value, and suppose this is the minimum value. The maximum value always greater than minimum value, and they are equal only in the case where function is constant function. So we know that the maximum value, that is least upper bound of the function in kth interval, is always greater equal minimum value, that is lower bound of the function in that in subinterval. So capital Mk maximum value always greater equal minimum value. So we have to use this condition in this formula. Okay. What is this formula? So lower sum is equal to sum mk delta xk. So small mk. Now small mk is less equal capital Mk. That is, we can write it as this value is less equal capital Mk. So we can write it as small mk less equal capital Mk. That is lower value less equal upper value. Use this condition here. So this becomes, now this equal to become less equal. Why? This m small mk is less equal capital Mk. This is less equal capital Mk delta x. What we have done, we have just replaced lower value by upper value. So this become greater equal. Why? This maximum value always greater equal minimum value. And what is this? This is the formula for upper sum. So this less equal u p here. So this implies lower sum is less equal upper sum for partition P of the function of the interval I corresponding to function f. Okay. So now, similarly, second theorem. This theorem, what we have to prove in this theorem? We have to prove that now lower sum is less equal to upper sum, but lower sum is always greater equal this value b minus a into m, and upper sum always less equal to m into b minus a. Now what is b and a? B and a are the endpoints of the interval. What is this m, small m and capital M? Capital M is nothing but the maximum value of the function in whole interval AB. What was capital M? Capital M was the maximum value of the function, but only in the kth subinterval. Okay, and here capital M is the maximum value of the function in whole interval. Okay, suppose this is the interval a to b, and this is the graph of function. Okay, so this is the maximum value of the function. We say it is capital M, maximum value in whole interval AB. But if we ask what value of M1, that is the maximum value of the function in first subinterval. Suppose it is first subinterval. So in this case, we will get capital M1, that is maximum value of the function in first subinterval. In this case, suppose this will become maximum value. Okay, so this is M1 and this is M. M means maximum value of the function in whole interval AB, and MK, for example, M1 means maximum value of the function in only first interval, or MK means maximum value of the function in kth interval. Similarly, small m only, this is minimum value of the function in whole interval AB, and small mk means minimum value of the function in kth interval, and only small m means minimum value of the function in whole interval. Okay, so again, now see, this is the maximum value of the function in whole interval, and this is the maximum value of the function in this interval. Now we have maximum value of the function in whole interval, that is m, is always greater equal maximum value of the function in sub interval. Okay, see, maximum value is the highest value. Okay, although this is the maximum value in sub interval, but this is greater than this value. So maximum value is always greater equal to maximum value in sub intervals. Okay, also minimum value is minimum value of the function in whole interval is always less equal minimum value of the function in sub intervals. Okay, suppose we take the example. Suppose consider example function f of x is equal to x squared. Okay, and we take the interval I is equal to 1 to 4. Okay, now what is the value of function at point 1? F of 1 is equal to 1, f of 2 is equal to 4, 2 is the square of 2. What is the value of f of 3? 9 square of 3, and f of 4 is equal to 16. Okay, so this is, so we plot the graph of the function. Okay, so we'll just plot the points. So suppose this is the interval. Our interval is from 1 to, so we take interval from 1 to 4. Okay, so 0, 1, 2, 3, 4. So at point 1, value is 1. So this is value is 1. At point 2, value is 4. So at somewhere here. At point 3, value is 9. At point 4, value is 16. So graph is like this. Okay, square. And so at point 1, value is 1. At point 2, value is 4. At 3, 9. And at 4, 16. So in this interval 1 to 2, M1 maximum value is 4. So capital M1 is 4. Capital M2 in this interval is square of 3, 9. Capital M3 in this interval maximum value is this, which is square of 4, that is 16. Okay. So these are the m1, m2, m3. Now, if we ask what is value of m, that is the maximum value of function in whole interval 1 to 4, and which is this value. Why? This function is increasing, and this is the maximum value. So m become 16. So you see, 4 is less equal 16, 9 is less than 16, and 16 is less equal 16. These two values are strictly less than m, and this is equal to m. So we have written maximum value is always get equal every mk. Okay. Similarly, if this is minimum value, okay. So this is, we will write now lower bounds or minimum value. What is small m1? It is the minimum value of the function in first subintervals. This subinterval minimum value at this point, which is square of 1, and which is 1. So m1 is 1. Now in this subinterval, second subinterval, minimum value of the function is at this point. See, this is the minimum, this is maximum in this subinterval, and this is the square of 2, that is 4. So small m2 is 4. Small m3. Okay. Minimum value of the function in this subinterval. See, here maximum, here is minimum. So minimum is nothing but square of 3, which is 9. So these are the minimum value of the function in these three subintervals. Now what is value of m, small m, which means minimum value of the function in whole subinterval 1 to 4. We can see that minimum value is at this point 1, which is 1. Why? Graph of function is increasing, so function is increasing. Minimum value is at 1, at point 1, which is 1. So m is equal to 1. See, 1 is equal to 1. Now 4 is greater than 1, 9 is greater than 1. So this means these small n kids are always greater equal small m. Okay. That is, see, this m1 and this m are equal. Other two values, 4, m2 is strictly greater than m. m is 1, m2 is 4. Also m3, 9 is strictly greater than 1. So these two relations are important for proving this theorem. Okay. Now we will prove this part. Okay. So we have given lower sum is equal to summation mk delta xk. Now we have verified that mk is always always greater equal small m. Small m always greater equal m. Minimum value over whole interval is always less equal minimum value over subintervals. So we use this condition here. So mk is less equal. Sorry, mk is greater equal. Okay, mk's are greater equal m. So we replace here mk by m. So we have to replace here equal to sign by greater equal. So this is greater equal sum m into delta xk. So it's greater equal small, we take m is the minimum value, constant we take outside. So m into sum delta xk. Now what is the sum of delta xk? That is sum of the all subintervals. That is length of the whole intervals. Now interval is from a to b. Its length is b minus a. This is greater equal m into b minus a. So lower sum always greater equal m into b minus a. So first part we have proved. Okay. Now in similar way we will prove this part. Okay. So write the formula for UPF first. Okay. What is UPF? Upper sum for a function corresponding to partition P, and its formula is summation of mk delta xk. Now we know maximum value of the function or whole interval is always greater equal maximum value of the function or some segments or subintervals. Okay. So replace here mk by m. Okay. Since m is greater equal mk, this becomes, so mk's are less equal m. So this equal to sign is replaced by less equal. Why? Mk is less equal m. So replace mk by m. So m into delta x. We just replace mk by m, and since mk are less equal to m, is equal to become less equal. Okay. This is less equal. Take m, which is maximum value, some constant number, into sum delta x. So summation delta x is nothing but the sum of the subintervals, and this summation is over all subintervals. So that is, it is nothing but the sum of length of whole interval, and again length of this interval is b minus a. This is less equal m into b minus. So at the, so we can write as u p f is less equal this. So combine this condition and this condition, you will get our required theorem. Okay, clear? Okay. Next important theorem is refinement of partition P increases lower sum and decreases upper sum. Okay, and decreases upper sum. So this is the next important theorem. That is, we have to prove if P is a partition and P star is the refinement of partition P, then lower sum of F corresponding to partition P is less equal lower sum of F corresponding to partition P star. तो क्या हम क्या देख रहे हैं यहाँ पे, अगर P जो पार्टीशन है और P स्टार उसका रिफाइनमेंट है, तो रिफाइनमेंट के बाद जो लोअर सम हम निकालेंगे वो ऑलवेज गेट इक्वल लोअर सम ऑफ F विथ ओरिजिनल पार्टीशन. ओके, और इसका उल्टा यहाँ पे होगा, अपर सम बिफोर रिफाइनमेंट जो ओरिजिनल पार्टीशन है, सो अपर सम ऑफ फंक्शन F विथ ओरिजिनल पार्टीशन P इज गेट इक्वल अपर सम ऑफ फंक्शन F विथ रिफाइनमेंट जो पार्टीशन हमने बनाया है P स्टार. ओके, सो आफ्टर रिफाइनमेंट हम अगर हम अपर सम निकालेंगे उसी फंक्शन का विथ रिफाइनमेंट पार्टीशन P स्टार, तो अपर सम डिक्रीज हो जाएगी और लोअर सम इंक्रीज हो जाएगी. देखो, आफ्टर रिफाइनमेंट लोअर सम इज इंक्रीज, बट आफ्टर रिफाइनमेंट अपर सम इज डिक्रीज. ओके, सो हमें प्रूव करना है. सो दिस इज one of the important theorem. Okay, so we consider P star as the refinement of P. So what is refinement? We just add some extra element to the original partition. So यहाँ पे क्या करेंगे? We add just only one element. Okay, so we consider P star as the refinement of P just by adding one element. हम सिर्फ एक एलिमेंट एक्स्ट्रा ऐड करेंगे ओरिजिनल पार्टीशन में. देखो, ये ओरिजिनल पार्टीशन P is a partition containing x0 x1 up to xn. ओके, वहां पे x0 क्या है? a, जो यहाँ पे इंटरवल हमने क्या लिया? इंटरवल लिया है I is equal to closed and bounded intervals a to b. Okay, this is our interval. This is P is the partition of this interval with x0 as a and xn is b. और these are the elements of partition. So ये partition है x0 x1, बीच में xi minus 1 xi और आखिरी में लास्ट एलिमेंट which is b, इसको हम नाम दिया है xm. ओके, सो ये ओरिजिनल पार्टीशन है. सो वी ऐड जस्ट वन एलिमेंट एक्स्ट्रा टू दिस पार्टीशन. ओके, समझो अभी ये जो इंटरवल है, इंटरवल xi minus 1 to xi, we add one point in between these two elements, so we add extra. So as we are adding one extra point to this partition, this become refinement of original partition. So this is the refinement of partition P. Now we will calculate lower sum with this partition, lower sum with this partition, and we will see that this lower sum with refinement partition is greater than previous lower sum of the function with original partition. Okay, so this is the partition, original partition. This is the partition after refinement. So for first original partition, subintervals are I1. I1 means first subinterval x0 to x1, I2, then later on xi minus 1 to xi, that is ith interval. Okay, up to so on. Similarly, For P star, subintervals are I1, I2, I minus 1. Okay. So up to this, all intervals same, but in this interval, we are adding one point, that is x star. So this interval is get divided into two subintervals again, xi minus 1 to x star and x star to xi. So this was previously this was the ith interval, xi minus 1 to xi. This was the ith interval. But after refinement, this subinterval get divided into two more subintervals. We give name to this two extra subinterval. We call this subinterval I star and another subinterval as J star. Okay. So these are the two subintervals. Now, so in this case, there are one extra subintervals are there. Okay. So this is the partition P, this is the refinement. These are the subintervals of partition P and these are the subintervals of partition P star. The only thing to observe here, we have divided this interval into two subintervals. Okay. So now we have to find lower sum and upper sum for partition P and partition P star. Okay. So for that purpose, we know the formula contains list upper bounds of function and greatest lower bound of the function in each subintervals and length of that subintervals. Okay. Now for partition P, what are the subintervals? I1, I2, then I minus 1, then ith interval, then I plus 1 interval, and last nth interval. For partition P, the intervals are first I1 same, I2 same, up to I minus 1. All the intervals are same. Okay. Now the problem is only here. Up to this, intervals are same. After that, intervals also same. I plus 1 to I plus 1 to I. Only difference is here the interval I. Here instead of interval I, we have divided this interval into two subintervals. One is I star and J. Other is J star. Okay. So we will find first lower sum with partition P. Before that, we will give some notation to the minimum value and maximum value of the function corresponding to these new subintervals. Okay. So we write capital H1 for least upper bound of function when x belongs to I star. Okay. We noted H1, capital H1 as the upper bound value, maximum value of function, but when function is in I star interval. Okay. And H2 as maximum value of the function, but when function is in J star. Okay. When function is in second subinterval J star, then this maximum value is we get notation, so we did not go it by H2. Okay. Similarly, H1 for minimum value of the function in I star and small h2 for minimum value of the function in J star. Okay. So capital H1, H2 for maximum value in I star and J star, and small h1, small h2 are notations for minimum value of the function in I star and J star interval. Okay. Again, we already seen that minimum value for these subintervals and minimum value over these subintervals and these subintervals. What is the relation? That minimum value is less equal minimum value over these two subintervals. Okay. So we are written that minimum value for function in I subinterval, that is in this subinterval, is less equal minimum value of the function in this subinterval and this subinterval. Okay. So mi is less equal h1 and mi is less equal h2, small m. Okay. Similarly, we already noted that maximum value of the function over whole interval is always greater equal maximum value of the function over short subintervals. Okay. So again, maximum value over this whole subinterval, that is mi, is always greater equal maximum value of the function in these two subintervals. Okay. So we have written that mi is greater equal to capital H1 and mi is greater than or equal to capital H2. Okay. These two are the most important points. Okay. So now what is the lower sum with partition P? Nothing but the sum of product of minimum value of the function and length of the interval. So suppose m1 is the minimum value in first interval and delta x1 is its length. So m1 delta x1 plus m2 delta x2 up to this interval, that is mi minus 1 I minus 1 interval. So mi minus 1 into delta x I minus 1 plus next interval is I. So mi delta xi, then mi plus 1 delta xi plus 1 up to mn delta x1. What we have done, just take the summation mi delta xi. Okay. Now here is some problem in writing such notation. Why? Because we have divided this interval into sub intervals and there we have given name to that I star and j star. These two names are we have given to this sub intervals. Okay. So we write lower sum with of same function f but corresponding to partition p star. Now since up to this intervals are same, so similarly m1 delta x1 m2 delta x2 up to I minus 1 interval. So up to mi minus 1 delta x I minus 1. Okay. Now next interval is I star. Okay. So and its length is x star minus x I minus 1. So length into minimum value is h1. So h1 into its length mi delta xi, but here we are not writing delta xi. Okay. So h1 into length of this subinterval is x upper value minus minimum value. So x star minus xi minus 1. Similarly, next interval is j star. So its minimum value of function is h2. So h2 into length of the interval. What is the length of the interval? X star minus x star plus. Now again next part is same because next intervals are same. So again same mi plus 1 delta xi plus 1 up to mn delta xi. Okay. So only difference is here. Here there is only one interval. Here there are two different intervals. Okay. Here maximum value is capital mi, minimum value is capital small mi. Here maximum value is capital H1. Here h2. Here minimum value is small h1. Here small h2. Only this is the difference. Okay. So now we will take difference between lower sum of the function corresponding to partition p star and lower sum of the same function of corresponding to partition p. Now since some terms are same here and here, in subtraction they get cancelled. For example, these terms are same, so in subtraction they get cancelled. Similarly, from this I plus 1 interval, terms are same. So also these terms also get cancelled in subtraction. So we will write here only remaining part. So remaining part is, so lower sum of refinement is written first. So we will write the remaining element from these terms. Okay. So here h1 x star minus xi minus 1 and plus h2 xi minus x star. Okay. So we write x star here. Sorry. Now minus remaining terms in lower sum of function here corresponding to p. Here remaining term is only one, is mi delta xi. So minus mi delta xi. Okay. So now we will write some. We will make some adjustment here. Okay. So we write h1 x star minus xi minus 1 plus h2 xi minus x star as it is. Okay. Now minus mi, we write delta xi. What is delta xi? Nothing but xi minus 1, xi minus xi minus 1. Okay. So this is equal to h1 x star minus xi minus 1 plus h2 xi minus x star. Okay. minus mi into. Now we will subtract x star and add x star here. Okay, so the term does not get disturbed. Okay, there is some adjustment only. So xi minus x star. So we have subtracted x star minus x star, but don't have to change this. So we have to add x star again. So plus x star and then minus xi minus 1 as it is. Okay. So we have done some adjustment here. Now take common parts here. X star minus xi minus 1. Here also x star minus xi minus 1. So mi into this term and h1 into this term. So this term is common here. So take it outside. So x star minus xi minus 1 into h1. Okay. Similarly, xi minus x star, and this is multiplication with mi. Again, this term and this term are common. Take it outside and write the remaining terms. So remaining terms are plus here. So here you are right h1 minus m1. Okay. Similarly, here h2 x, here this term is common, xi minus x star, and remaining terms are h2 minus mi. Okay, h2 minus m. Now we can see x star minus xi minus 1. See, x star is ahead of xi minus 1. That is, x star is greater than this term. So difference is positive, greater or equal 0. Again, h1 minus mi. Here already seen h1 is greater or equal mi. h2 also greater or equal mi. So both these terms are also greater or equal 0. That is positive. And this term xi minus x star, again xi minus x star, xi is ahead of x star. So xi is greater than x star. So this difference also greater or equal 0. So the each term in this four terms is always greater or equal 0. So this multiplication and this addition is total addition also greater or equal 0. This becomes greater or equal 0. That is, this difference is greater or equal 0. So LP star f minus LP f is greater or equal 0. That is LP star f, that is lower sum of the function f corresponding to partition P star is greater or equal lower sum of the function f with partition P. Okay, so this is the proof. Similarly, we can prove that after refinement, upper sum decreases. That is, upper sum for the same function f over partition P is greater or equal upper sum after refinement. That is, upper sum of the same function f with partition P star. Okay, so thank you. Stay safe.